Hello everyone, I am Sixun Huang from National Kaohsiung University of Science and Technology, Taiwan. Today, I want to talk about a real-time background subtraction algorithm using Colebooker model. This algorithm was proposed in the paper entitled as Real-Time Foreground Background Segmentation using Colebooker model in 2005. The outline of this lecture includes introduction about the idea of the proposed algorithm, Colebooker definition about what the Colebooker is and its ingredients, Colebooker construction about the process to construct a Colebooker for representing the background scene, subtraction process about the way to subtract the background from the observed image using the constructed Colebooker. Based on the assumption that the camera is stationary, the objective of the background subtraction is to segment the region of interest or coded foreground from the background scenes. The pictures in the first row are the original images. Those in the second row are foreground masked by subtracting the background from the original images. In general, the algorithm for background subtraction consists of modeling and the subtraction process. For giving a sequence of background images, modeling process constructing a model for describing background scene. Subtraction process subtracts the background from the currently observed image so as to obtain the foreground mask. The major challenge in background subtraction is dynamic background. Dynamic background refers to the scene containing non-stationary background objects. This makes it unfeasible to model intensity of a point by a unimodal distribution. For example, with a scene containing a waving tree, the objects appearing to this point may be leaves or skies. Accordingly, its intensity distribution should have two modes, respectively for leaf and the sky. In the literature, the models widely used to handle dynamic background are Gaussian mixture models and the non-parametric model. The use of GMM is to approximate the actual distribution by the use of several Gaussians. For example, this distribution can be approximated by two Gaussians. The advantage of the GMM is that only a few model parameters are needed for modeling. But assuming the distribution of any background point as a mixture of Gaussians is unrealistic. The idea of non-parametric model is to approximate the actual distribution by the use of periods of samples. The more the samples locate, the higher the probability is. The advantage of non-parametric model is that it relaxes Gaussian assumption and makes modeling arbitrary distributions possible. For accurate approximation, it is necessary to store long periods of samples, but this wastes of memory. Accordingly, the approach proposed in this work is a hybrid of GMM and non-parametric model. Similar to non-parametric model, this work approximates distributions by a set of samples to relax Gaussian assumption. Instead of storing all samples, this work describes the sample set by a compact form called the Colebook, similar to the Gaussian distributions used in GMM. More specifically, the samples with similar intensities will be grouped together to form a cluster, which can be described by a few parameters. Here, we give the definition of a Colebook. Let S1, S2 to Sn be a sequence of n background RGB vectors of a single point. A Colebook B is used to describe the sequence by allo cohorts C1, C2 to CL. Each cohort stands for part of background RGB vectors. For example, there is a background sequence of 8 RGB vectors. If these background samples are partitioned into 2 clusters, a corpus consisting of 2 cohorts is used to describe this background sequence. Each cohort stands for a cluster. For example, a cohort C1 stands for X2, S3, and X7, and the cohort C2 is for the others. A cohort is used to model the sequence of RGB vectors in the ice cluster. It models intensity as well as temporal properties. A cohort Ci is composed of 2 attributes, Vi and the auxiliary AuSi, where Vi is the mean RGB vector of all samples in this cluster, and the AuSi is a tuple consisting of 6 elements. The first 2 terms are the mean and the maxima brightness. Fi is the number of samples in this cluster. Lambda is the maxima negative round length. That is the longest interval that this cohort has not recurred. Pi and Qi are the first and the last access time respectively. For example, for a cluster consisting of 3 RGB vectors, we firstly compute their brightness according to this equation. The mean RGB vector of this cluster can be expressed as this equation, and that's equal to a vector of 1, 6, 1. The minima and the maxima brightness are 5 and 7 respectively. The frequency f is 3 because there are 3 samples in this cluster. Since the longest time interval that this cohort has not recurred is from the time 3 to 7, so the lambda is the 7 minus 3 equal to 4. The first and the last access time P and Q of this cohort are 2 and 7. After introducing the definition of a cohort, we next talk about the process to construct a corpus. Given a sequence of n training RGB vectors of a point, the output of construction process is a corpus consisting of allo cohorts C1, C2 to CL for modeling background scene. For reducing computation complexity, an incremental clustering algorithm is firstly applied to obtain a set of cohorts. Since the sequence for training is not foreground-free, some of the resulting cohorts may represent moving foreground objects or noise. Hence, the corpus construction has the second step that selects the cohorts representing static and dynamic background points. The steps for incremental clustering algorithm are described as follows. Firstly, the corpus B is initialized as empty set. At iterative step, we sequentially match observation ST to all cohorts in B. If there is no match, we create a new cohort to represent ST. Otherwise, we update the first matched cohort CM using ST and move it to the first cohort in B. The definition of a match of ST to a cohort is deferred to the next discussion. In case with no match, the created cohort C for describing ST is set as follows. Since cohort C only has one observation ST, its V average RGB vector is set as the same as XT. The minima and the maxima brightness are both the same as that of ST. Frequency is 1. Maximum negative run length lambda is current time minus start time. The first and the last access time P and Q are both the current time T. For example, at time 2, no cohorts mass S2, whose RGB vector is 170 and the brightness is 7. The V of the newly created cohort is the same as S2, equal to 170. Minima and the maxima brightness are both 7. Frequency F is 1. Lambda is 2 minus 1 equal to 1. The first and the last access time P and Q are both 2. In case with match found, we update the parameters of the first matched cohort Cn by St according to these two equations. The numerator is intensity sum in R channel until now, sum before update plus RT. The denominator is the total number of observations matching Cn. The minima and the maxima brightness are updated through min and max operators of those before update and the current brightness of IT. Frequency F is added by 1. Maximum negative run length is the max of lambda before update and the current time T minus the last access time Qn. First access time is unchanged and the last time is updated as current time T. For example, if the current observation S3 with RGB vector 052 matches the cohort Cn, we update Vn by S3 according to aforementioned equation, and the Vm equals to 0.561. Similarly, we update AUX as this equation. After simple calculation, we got the updated AUS. By visiting all training samples sequentially, we can obtain a set of cohorts. However, some of the obtained cohorts may represent the moving foreground objects. Accordingly, the next step of cohort construction is to select the cohorts for the true background, including static and dynamic background points. For a point on the tip of the tree, the picture shows its intensity distribution. The points in blue, green, and orange rectangles are sky color, tree color, person color, respectively, and each of which is modeled by a cohort. Sky points appear most of the time, and its cohort has very small lambda, about 15. Tree points appear quasi-periodical, and its cohort also has a small lambda, around 100. However, the lambda of the cohort for person body is large and about 240. According to this analysis, we observe that the true background is quasi-periodic. That is, values recur in a bounded period. Thus, the rule to select background cohorts is to take the ones with small lambda. Here, T is a threshold for selection. In this paper, it is set as half the number of training frames. That is n over 2. So far, we have constructed a codebook consisting of cohorts for describing background point. Before to describe the subtraction process using the constructed codebook, we firstly introduce the color model of a cohort. By observing the intensity of these 4 points in color chart under illumination variation, the shape of this point intensity distribution as shown in this picture has two attributes, elongated and toward origin. Accordingly, the color model defined by a chord is a cylinder. Vi defines the major axis of the cylinder, and a constant gamma defines the cylinder radius. Top and bottom bases are determined by using maxima and minima brightness of the chord according to these two equations, where alpha and beta are two constants. In this paper, alpha and beta are in the range from 0.4 to 0.7 and from 1.1 to 1.5 respectively. With this color model, the match of a sample X to the chord Ci is denoted as M of Xci equal to 1, and is defined as that X is inside the Ci-defined cylinder. It has to satisfy these two conditions. The distance from S to Vi, d color of Svi is less than cylinder radius gamma, and the length of X is between two defined cylinder bases I super low and I super high. According to Pythagorean theory, d color of Xvi equals to this term, where L is the length of this black line segment. Moreover, according to basic geometric, L square equals to this term, and the angle bracket here denotes inner product. For a point S, it is classified as background if at least one chord is matched. Otherwise, the label of X is foreground if none of chords are matched. For example, there is a point X whose background intensity distribution is represented by two chords, C1 and C2. It has label B if it matches to at least one chord C1. It has label F if it matches neither C1 nor C2. In this lecture, we detail a background subtraction algorithm using a constructed chord book. Thanks for your listening and have a nice day.